for homework.
I think what's more impressive.
Can the two that we do for homework be
through a
two
lot
out
of
of the book?
pages of paper? I know that staple is like broke. So like no, we don't have any more like test grades to go get rid of these findings, right?
It's not, you didn't flip it though.
Oh, I don't know. Same way.
Next. Onwards!
Still not quite good enough.
It's never good.
So,
like
like,
my question before you
can our two response questions at home be the ones out of the...
There are book practice ones in this little packet.
That's so nice of you.
If you tell me yes, I might scroll out of those right now.
What was your question?
I asked, are we gonna have any like test grades going
Oh,
into
oh. I still haven't put in the take-home test that we did a week ago.
Oh, I can get on that.
I don't remember
So,
it at all.
I
don't remember that. I just wanted to tell you.
It was like an egg puzzle.
Yeah, it was that Friday that I wasn't
Oh,
here.
the question.
Yeah, and then
Oh,
there
okay.
were
I don't
two response questions that we said we take-home test.
Are you gonna
But you
do
still
like?
have me over last.
I know. My mastery level is like Christmas over here. With all these reds.
So remember, you can do extra practice out of the AP book to get bonus points.
I'm not even doing that.
We haven't had a lot of grades this 9 weeks, so bonus points would go a long way. Do extra practice problems.
Oh, but I have some bonus.
I have a question. So,
I know what it has.
if, like, for those, the book practice, do we have to have, like, the right answer for all of them?
Well, you have the
I
answers.
know, but, like, some of the answers they have, I did work and I did not get it. So, like, if I show that I tried, does that give me something?
Yes, but then I want you to ask me questions on.
Okay, but there's, like, we literally don't have enough time today for me to ask a question. Basically.
Yeah,
You said you were going to come in 8th period.
Yeah, that 45 minutes is not enough because
Well, 45 minutes a day, all week.
that I'm not here on Tuesdays and Thursdays, or I'm not going to be here Friday, and I'm not going to be here in class or Friday.
Are you going to come in Thursday 8th period?
I can't, because I have job shadowing. See, we're running out of time for that.
Yeah, we're
Well,
like
then-
Friday.
Text me questions.
Wait.
Remind.
Oh yeah. By the way, my classes here have remind.
Alright, we're going to look at 2 types of free response questions each day this week. Okay? Today, we're going to look at first rate and accumulation functions. Okay? These are the in and out problems that we looked at fairly recently, where you're given a function that models some rate of something going in, and then another function that models the rate of something going out. Okay? This has shown up on the AP test as a free response question every year for the last 6 years. So odds are you're going to see a problem like this on the free response part. Cheesing about. Yes.
Sharon, you got this. I'm gonna get a 3.
Alright. Yes. Yes, you are. The big idea is that the integral of a rate function is an amount. So if you are given a rate, you integrate the rate to get an amount. We will look at the most common application of this is position, velocity, acceleration, right? If you integrate a velocity, you get a position, but they can apply this to any type of rate function, right? So I'm not going to read through all these bullet points. This was a resource that I found online that does a good job of telling you exactly what you need to be able to do for these types of problems. I'm not going to read through all these. I think it's more important just to go through some practice problems together. All right, so let's take a look at this first one here. Okay, the penguin population on an island is modeled by a differentiable function p. And let's see, there are 100,000 penguins on the island at t equals 0. So That's my initial value, right? We start with 100,000, and then we've got some rates, or some rate functions that tell me birth rate and death rate. Okay, so these are rate functions. This is the rate at which penguins are being born. This is the rate at which penguins are dying. Part A just says what is the rate of change of the penguin population on the island at t equals 0. So if I've got a birth rate and a death rate, how would I figure out the rate at which the penguin population is changing? Just the birth rate minus death rate at t equals 0. Right? These are already the rates, so I'm not differentiating, I'm not integrating, I'm just finding b of 0 minus d of 0. Right? And this was a calculator problem. Okay, so we can just plug this into the calculator. So 1,000 times e, we would end up with just e to the 0 minus 250 e to the 0. So I guess actually we hopefully can do this without a calculator.
Yeah. I was thinking like
You still should be able to do that without a calculator.
but definitely just be not being able to add subtract. Okay, so I don't know. It's been a long
Mia's
week.
having a rough day though. So.
I'm having a rough week. It's been
Okay, let's continue.
I've been like last week.
All right. So what would my units be? 750 what?
Penguins.
Penguins per year. This is still a rate, right? So this is penguins per year. That's the rate at which the penguin population is changing. B, to the nearest whole number, what is the penguin population on the island at t equals 40? How would I do this one? We need to integrate. What do I need to integrate?
Birth rate minus death rate.
So
Good boy.
I'm going to have b of t minus d of t dt. And remember, on a calculator problem, when you're showing your work, you can just write b of t and d of t. You don't have to write out the whole function if it's a calculator problem. Okay, now, what would my bounds be? 0 to 40. So is this going to get me the entire population?
No, you have to add the initial value.
Right. This is the change in population. I have to add the 100,000 onto this. So 100,000 plus this integral will get me the total population. So what do we get? We plug that into the calculator.
Well, it's- 0.329.
That's what
133,058.
Oh my god.
So pay attention to what it asks you to do. So part B says to the nearest whole number. We're rounding to the nearest penguin. So 133,058 penguins would be the population on the island at t equals 40. Okay, then C says to the nearest whole number, what is the average rate of change of the penguin population? How do I find average rate of change?
1/4 minus 1.
Average rate of change is the slope between 2 points. Average value is what you're thinking of. Okay? Average rate of change is going to be the slope between 2 points. So I want the penguin population. Okay, so what we've found so far is that at p equals 0, or at t equals 0, sorry, p of 0 is 100,000. And at t equals 40, we've got a population of 133,058. So to find the average rate of change, I'm just going to do 133,058 minus 100,000 over 40 minus 0. That'll get me the average rate of change over this interval from 0 to 40. So what is that?
826.
826.
Yep.
What are my units?
Penguins per year.
Penguins per year. So then the last part says find the absolute minimum penguin population on the island. Show the analysis that leads to your answer. How do I find absolute mins or maxes?
Well, the slope changes.
Right, find where the slope changes, meaning where the slope would equal 0, or where the rate. Right. So what is my derivative? What is my rate function here of the penguin population?
Birth rate minus death rate.
Birth rate minus death rate. So I want to find where b of t minus d of t equals 0. And again, this is a calculator problem. So what would be the best way to find this using the calculator?
When they intersect.
Where these two functions intersect. So we can graph both of these functions, see where they intersect on the graph.
Yeah, we get like that. Very
Whoa, 10,000. That might be a little
big.
too big.
Thank
So,
you. Like, we seriously can't see it.
well, remember you can do zoom 0. That'll at least get the graph, or a picture of the graph on there somewhere. It may not be a good window, but it'll at least get the graph on there, and then you can adjust from there.
I could see part of my graph.
Okay.
Well, not now, because I just didn't figure something earlier.
Ooh, hey, I see part of my graph.
So remember, if we're thinking about, this is the x value, right? And we only care about 0 to 40. So it might make sense to make our x window 0 to 40. And then we can adjust our y window from there. So Are we comfortable doing that?
I know how to do it.
Are we trying to do that? Sharon, you're sitting there on your phone too. What are you laughing at?
Yeah, sorry. I know what you're doing though. He doesn't.
Will that help?
My grass.
This is like a brick wall.
Yeah, it's
Spider-
okay.
it's like the Spider-Man meme where they're pointing at each other. Like,
It's not working.
Wait. That's a graph. That's a graph.
Alright, so what we should find is that these two graphs intersect at 34.657359. Okay? So this is my, there we go, good job. This is my only critical point, okay? The only place where these two intersect. Now, if we are finding absolute mins and absolute maxes, what other points do I need to look at?
Endpoint.
Endpoints. So I need to plug this value and 0 and 40 into the population function to get, excuse me, to get my possible values. Well, we already know that the population at 0 is 100,000, right? And we already found that the population at 40 was 133,058. So then we just need the population at this one, at 34.657359. How would I get that?
Put that value in.
To what?
And do that.
This one, right? So I'm going to evaluate the integral from 0 to 34 point whatever of b of t minus d of t. So 100,000 plus this integral. 34 point whatever of b of t minus d of t. Get 139,166.667. So what's my conclusion then? What is my absolute min and what's my absolute max? Right. The minimum is 100,000. Maximum is 139,166.667. Remember, if we are saying what is the population, what is the absolute min or max, we're looking at the y value. If we're saying where does that occur, we're looking at the x value. So if we're saying find the minimum penguin population, we're looking for that 100,000 value. Questions on something like that?
Oh, there's the answer to that.
Yes, so the scoring rubric is the next page. Okay, we can see how this question was scored. Okay, so part 1, finding that 750 was just worth a point. Part 2 said our integral was worth 3 points. Okay, 1 point just for having the correct limits. So if we just said the integral from 0 to 40, that was a point. Right? Another point for then having the correct integrand. Okay, that's just this part on the inside, b of t minus d of t. And then a third point for having the correct answer. So adding the 100,000 onto the integral would be part of that answer point. Okay, so even if you're struggling figuring out what to do, even what function to put in here, if you just set up the integral from 0 to 40, that was a point. Okay, so remember, this is just about accumulating as many points as possible.
My answer would have worked for C, because that's what they did.
Yeah, if you do the average value of a rate, that would be the same as the average rate of change of the original function. Right? And that part C then was only worth 1 point, setting that average rate of change up, and then part D was worth 4 points. Okay, 1 point just for setting B of t minus D of t equal to 0, 1 point then for getting this value, 1 point for finding that this is the absolute min, and 1 point for finding that this is the absolute max. Questions on these types of problems? All right. We're not going to be able to get through 4 of these in a day. I mean, on the first 30 multiple choice, no. On the next 15, yes. On the first 2 free response, yes. On the final 4 free response, no. It's just like AP test. I mean, it tells you in there which ones you can and can't, right? Yeah, we're going to treat it just like the AP test. All right, so let's skip this one for now and go ahead and go to type 2. Okay, particle motion. Okay, this is another fairly recent idea that we've talked about, and we talked a lot about this when we did the multiple choice stuff last week as well. Okay, but the big ideas with particle motion are that velocity is the derivative of position, and acceleration is the derivative of velocity. If I integrate a velocity function, I will get displacement or net distance. If I integrate the absolute value of a velocity function, I will get total distance traveled. Okay, those are kind of the big ideas. So to put those together, right, we could have something like this. Now, about half the time they give you a table, half the time they give you a function. Okay, so we need to be prepared for both of those situations. So we're given a table that models Ruth's velocity when she's riding her bicycle from 0 to 2.4 hours. And we always know that velocity is greater than 0. Okay? If velocity is always greater than 0, that means she never stops. Okay? Part A, we want to approximate Ruth's acceleration at 1.4 hours. Well, we don't have any values at 1.4. How would I approximate the acceleration at 1.4?
Don't you do like 16.3 minus 17.2 over 1.6?
Yeah, so we know that acceleration is the derivative of velocity, right? Meaning acceleration would be the slope of our velocity curve. So I'm just going to set up the slope of 0.1 minus 0.2. So we can say, oh yeah, with a function like that, yeah, this would have definitely been a calculator problem. So 16.3 minus 17.2 over 1.6 minus 1.2.
Negative 2.25.
What would my units be?
Since this is slope, miles per hour.
This is the slope of velocity.
Miles per hour per hour.
Miles per hour squared, or miles per hour per hour. Right. Part B, it says, using correct units, interpret the meaning of the integral from 0 to 2.4 of v of t dt. So first, what would that mean?
It is the position.
What is the integral of a velocity function? What does that get us?
Position.
Position.
It's the position. It's the net distance.
Yeah, net distance or displacement. We can use either of those terms. So this integral means the net distance or displacement, however you want to say it. Okay, and we would want to write that out in a sentence. I'm not going to spend the time writing it all out, but we would want to say, this integral is the net distance traveled from t equals 0 to t equals 2.4. I guess I can write that much out. T equals 0 to t equals 2.4. Then approximate this integral using a midpoint Riemann sum with 3 subintervals. How do I do a midpoint Riemann sum?
You take the point in the middle between 0 to 0.8, 0.8 to 1.6, 1.6 to
Right, those would be my 3 subintervals.
and then the middle value is the value you use
For
one of your sides.
right, so I'm just creating the area of 3 rectangles here. Right, so the first one will have a width of 0.8, and the height will be 11.8. So my area here, so I'm going to say the integral from 0 to 2.4 of d of t dt is approximately equal to my Riemann sum approximation. So 0.8 times 11.8 plus my second rectangle would also have a width of 0.8, or 0.8 to 1.6. And then its height would be 17.2. And then my third would also have a width of 0.8 and a height of 16.8. Right? Remember, that's it. Do not do the arithmetic. Stop there. Do not simplify. Right? Once you have an all numerical answer, just stop. Okay? Do not spend time simplifying. Do not try to make mistakes simplifying.
I mean, you wouldn't be trying to make mistakes.
Right, but it's time that you don't need to spend on it, and it gives you another chance to mess up. So don't do it. Part C says that Ruth's velocity can be modeled by this function. According to the model, what was Ruth's average velocity during the interval 0 to 2.4? If I'm given velocity, how do I find average velocity? Fraction. Yeah. So I would set this up as the integral from 0 to 2.4 of 1 over 2.4 minus 0, or I said times 1 over 2.4 minus 0 of this function. 24t plus 5 sine of
Can we just put g of t?
6t. Yes, since this is a calculator problem, we could just put g of t dt. Right? And remember, don't forget your dt.
Or someone shall smite.
Or someone shall smite you.
Wait, aren't you? Wait,
Oh, that makes sense.
$25.222.
So the way you set this up, I'm guessing you didn't have the fraction somewhere in the right spot. 14.064 miles per hour. Part D then says, according to the model,
Got it. Okay.
Is Root's speed increasing or decreasing at t equals 1.3? Justify your answer.
Speed is the absolute value of velocity.
Speed is the absolute value of velocity. But how would we figure out if that's increasing or decreasing?
You have to take more than one.
How did we figure out if speed was increasing or decreasing? I was trying.
He doesn't want to let me down hard.
In order to figure out if the speed is increasing or decreasing, we need to find both the velocity and the acceleration at that point. If velocity and acceleration have the same sign, speed is increasing. If velocity and acceleration have opposite signs, speed is decreasing. So, we need to find g of 1.3. So we're saying g is the velocity, and then I need g prime of 1.3. That would be the acceleration. Right? The derivative of this velocity function would be acceleration.
Isn't there a button that does that?
There is a button that gets you the derivative.
Is it math?
Math 8, yes.
Yeah, I'm just gonna. I'm not even.
You know how to do it though?
Yes.
All right,
Math 9 and math 8.
Because over actually put in 1.3, right?
correct. Yeah, so for g prime of 1.3, which would be the acceleration, we get 3.761. Yeah, all we really care about in this situation is whether it's positive or negative. Right?
It's
We get that both the velocity and the acceleration are positive. So what's our conclusion? Therefore, Root's speed is increasing. Okay, so we would want to write out that sentence. Okay, since it says give a reason for your answer. Since velocity and acceleration have the same sign, Root's speed is increasing at t equals 1.3. So these are the first two types of free response questions that are pretty common. Okay? The accumulation function or rate functions, okay, where most of the time you're given a function that models the rate of something going in and the rate of something going out. The one we looked at was birth rate and death rate. And then the second type is particle motion, okay, where you could be given information in a table or you could be given information function. I think we've got enough time here to look at the second particle motion example on here. So in this one, we're given a function instead of a table. Now, the majority of the time, you will be given information about the velocity. Right? So in this example, we're given a velocity function. You do have to pay attention, though. Sometimes you will be given a position function instead of a velocity function.
just to screw with.
Yeah, just to screw with you. Okay, the majority of the time it's a velocity function, but pay attention. Okay, it's not always a velocity function. So in this one, the prompt is pretty straightforward. Okay, particles moving along the x-axis between 0 and 12 seconds. Here's our velocity function, and then we are given an initial value, okay, or initial condition. The particle is at -2 when t equals 0. So part A, when is the particle moving to the left? How do I know when a particle is moving to the left or to the right? When what's negative? When velocity is negative, the particle is moving to the left. So this one was a non-calculator problem.
No.
How would I do this without a calculator?
Plug in that.
No. So what would have to happen for a particle to change direction? The slope of position would have to change, meaning velocity would have to change sign. Or in between changing sign, velocity would have to cross the x-axis or equal 0. Right? So what we want to do is find where velocity equals 0. Right? So how would I find where cosine of pi over 6t equals 0? So where does cosine equal 0? Pi over 2 and 3 pi over 2. So what we're saying then is pi over 6t equals pi over 2, and pi over 6t equals 3 pi over 2. And that's how we would solve a problem like this. So, yeah. So we can see pi over 6 times 3 would be pi over 2. So t equals 3 is one of my zeros. 9. So these are the zeros of my velocity function. Now what?
Sign chart.
Sure, make a sign chart. So we're starting at 0 and ending at 12.
If you
Yes.
plug in 3, it'd be 1 over 2, plug in 9.
So Ruby just kind of did it in her head. But what we could do to get t by itself, I would multiply by 6 over pi. 6 over pi, so the pi's cancel, we get 18 over 2, 9. Okay, so my sign chart then, okay, in between 0 and 3, is cosine of pi over 6t, positive or negative? You think?
I'm not good with my unit circle, okay? Because I plugged in 1, that'd be 6 over pi, and that's here.
Right, so in between 0 and 3, if we take a value, say 1, and plug it in, cosine of pi over 6, that's going to be over here on the unit circle, that's going to be a positive cosine value. How about between 3 and 9? It's going to be over here on the unit circle, right? So that's going to be a negative x value.
I'm going to have something down.
Right, it'll be over here. So that'll be a positive x value. So how do I answer the question? When is the particle moving to the left?
From 3 to 9.
From t equals 3 to t equals 9. And the particle is moving to the left from t equals 3 to t equals 9 because that's where velocity is negative. Part B, write but do not evaluate.
Yes.
Remember, these show up on the non-calculator portion. An integral expression that gives the total distance traveled by the particle from 0 to 6. How do I set up total distance?
Isn't it just the integral?
The integral of what?
The velocity.
So from 0 to 6, right? We're told those are our bounds. Not just the velocity. No, that's average value. The absolute value of velocity.
And do we have to worry about our initial position? The initial thinking?
Nope, because we just want total distance, not final position.
Okay, so C.
C, find the acceleration of the particle. And then is the speed increasing, decreasing, or neither at t equals 4? So acceleration would be the derivative of velocity, right? So v prime of t, how would I take the derivative?
You don't.
This one's pretty straightforward to take the derivative of, right?
Sine
Derivative of cosine is negative sine. So negative sine of pi over 6t
multiplied by the
times the derivative of the inside.
So
So that would just be pi over 6.
and then you plug it.
So, yeah, let's plug 4 into my acceleration. So negative sine of 4 pi over 6. Oops. Times pi over 6. So what's sine of 4 pi over 6? Yeah, 2 pi over 3. So really, yeah, all we care about is whether it's positive or negative. So is sine of 2 pi over 3 going to be positive or negative?
Oh, sine is positive.
Sine is positive, right? So we're looking at the y value. So we've got a positive value times a positive, but a negative sign out front. So this is going to be negative, right? So I don't actually care about what the value is, right?
So it is decreasing.
Well, what's v of 4? We still need v of 4, right? So what's the cosine of 4 pi over 6?
It'd be negative.
That's also going to be negative. So both the acceleration and the velocity have the same sign. They're both negative. Therefore speed is increasing. And finally, the position of the particle.
So we
We integrate our velocity function. So if we want at t equals 4, my bounds would be 0 and 4 of cosine of pi over 6 t dt.
Don't you need the initial position?
Right, so this would be my change in position. I would need to add the initial position to this. So negative 2 plus this integral. And this one was non-calculator, so we would have to do this by hand. There are 2 practice problems at the end of this. Okay, one for rate of change, one for particle motion.